In this video, we'll be learning how to calculate the average rate of change for a function. Now, when we talk about average rates, we always need to provide an interval for us to look between. From our last video, we learned that if we want to calculate the average rate, we want to look at the secant line connecting the two endpoints of the interval, and specifically, we want to calculate the slope of that secant line. So let's draw a picture to see what's going on. Suppose that we have a function named f whose graph looks like this. Let's say that we want to find the average rate of this function on the interval a to b, meaning we want to look between the x value a and the x value b. At those x values, we have the following points on our graph. At this point here, we know that the x-coordinate is a. The corresponding y-coordinate would be the output of the function at a, so we call that f of a. So the point has coordinates a, comma, f of a. Similarly, at this point, we know that the x-coordinate here is b. The corresponding y value would be the output of the function at b. So our second point here has coordinates b, comma, f of b. Now, if I want to find the average rate of change for my function on the interval from a to b, I need to look at the secant line connecting those 2 points on our graph, which looks like this. Again, what we learned last video is that the slope of this secant line is the average rate of change. So let's try to find the formula for the slope of this secant line. We'll start by figuring out what the rise and the run are. The run would be the horizontal distance between our 2 points. The rise is the vertical distance between our 2 points. We can compute the rise by doing y2 minus y1, and the run by doing x2 minus x1. For the rise, y2 minus y1 would be f of b minus f of a. For the run, x2 minus x1 would be b minus a. So for our function f here, the average rate can be calculated by doing rise over run, which is f of b minus f of a divided by b minus a. So this here is the formula to find the average rate of change of our function f on the interval a to b. Let's now get some practice with some examples. For these examples, we want to find the average rate of change for the given functions on the given intervals. After we find the average rate of change, we'll find the equations of the secant lines. In example A, we're working with the function f of x equals x squared on the interval -1 to 3. We'll start by looking at the graph of this function just to give us a sense of what we're working with. This step isn't necessary, but it'll help us tie in some of the concepts we've learned so far. If we were to graph the x squared function, the graph looks something like this. You can always verify that this is the correct graph by making a table of values. Now what we want to do is look at our function on the interval -1 to 3. So we'll start here at -1 and go all the way here to x equals 3. At those x values, we have the corresponding points. At -1, we have a point there, and at 3, we have a point here. Remember that we learned that the average rate of change for a function is the slope of the secant line that connects the two endpoints of our interval. From our previous page, we learned that the average rate is given by the formula f of b minus f of a divided by b minus a, where a and b are the endpoints of our interval. So in this case, a is -1 and b is 3. So what we want to do is compute f of 3 minus f of -1 divided by 3 minus -1. Since our function is the x squared function, we have 3 squared minus -1 squared divided by 3 minus -1. So we get 9 minus 1 divided by 3 minus -1. In the numerator, that's going to be 8. In the denominator, that's going to be 4. 8 divided by 4 gives us 2. So 2 is the average rate of change for our function on the interval -1 to 3. And what this means is that for our x squared function, on the interval from -1 to 3, if we increase the x value by 1, on average, we increase the output or the y value by 2. Now that we found the average rate, let's try to find the equation of the secant line. Remember that if you want to find the equation of any line, you need two things. You need a point and you need a slope. For the point of our secant line, we could choose either this point at x equals -1 or this point at x equals 3. Let's say we choose the point at x equals 3. We know here that the x-coordinate of this point is 3. To find the corresponding y-coordinate, we plug in 3 into our function to get the output. Since our function is the x squared function, we plug in 3 in, we get 3 squared, which gives us 9 as the corresponding output. So our point here is 3, 9. As for the slope of our secant line, well, that's the same as the average rate of change. In this case, we found that already to be 2. Once you have the point and the slope of the line, you can write down the equation in point-slope form, which is y minus y1 equals m times x minus x1. So plugging in the appropriate values, we have y minus 9 equals 2 times x minus 3. If we want to write this in slope-intercept form, all we have to do is solve for y. So let's start by distributing the 2. We get y minus 9 equals 2x minus 6. And then lastly, add 9 to both sides. We get y equals 2x plus 3. So the equation of our secant line is y equals 2x plus 3. Now let's take a look at example B. Here our function is g of x equals square root of x, and we want to find the average rate of change on the interval from 1 to 9. Again, we'll start by looking at the graph of this function, even though it's not necessary. If we graph the square root function, we get something like this. Again, you can verify the shape by making a table of values. We're interested in finding the average rate on the interval from 1 to 9. So let's find those corresponding points on our graph. At x equals 1, we have a point here. At x equals 9, we have a point here. Now remember that the average rate of change for our function on the interval from 1 to 9 is going to be the slope of this secant line that connects our 2 points. According to our formula, our average rate is going to be g of b minus g of a divided by b minus a, where a and b are the endpoints of our interval. So in this case, our a is 1 and our b is 9. So we're looking at g of 9 minus g of 1 divided by 9 minus 1. So let's try to compute this. Since our g is the square root function, we're working with square root of 9 minus square root of 1 divided by 9 minus 1. Square root of 9 gives us 3, square root of 1 is 1, divided by 9 minus 1. In the numerator, 3 minus 1 gives us 2. In the denominator, 9 minus 1 gives us 8. So we have 2 divided by 8, which is 1/4. So the average rate of change for our function is 1/4. What this means is that on the interval from 1 to 9, for our function, every time we increase our input or our x value by 1, on average, my output or y value is going to increase by 1/4. Now that we have our average rate of change, let's find the equation of the secant line. Again, if I want the equation of any line, we need a point and we need a slope. For our point, we can choose either the point at x equals 1 or x equals 9. This time, let's choose the point at x equals 1. We know that the x-coordinate here is 1. The corresponding y-coordinate would be the output of my function when I input 1. So plugging 1 into the square root function, we get square root of 1, which is also 1. So our point here has coordinates 1, 1. The slope of our secant line is what we found for our average rate. It's going to be 1/4. Now that we have a point and a slope, we can write down the equation of the line in point-slope form. Y minus y1 equals m times x minus x1. So plugging in the appropriate values, this gives us y minus 1 equals 1/4 times x minus 1. If we want to write this in slope-intercept form, all we have to do is solve for y. So start by distributing the 1/4. We get 1/4 x minus 1/4. And then lastly, add 1 to both sides. We get y equals 1/4 x. And then if I have negative 1/4 and I add 1 to it, I get positive 3/4. So the equation of our secant line is y equals 1/4 x plus 3/4. So in this video, we've learned how to find the average rate of change for a function on a given interval, and we also learned how to find the equation of secant lines.